In this video, we're going to look at different types of products. We call them special products because we'll look at difference of squares and perfect square trinomials, and we'll see how each of them are special in their own right of how they factor. There's patterns to how they factor, and we're going to look at those with different types of problem sets. So with these five, we'll start with the first one, and each problem will have a slide. You've got 16x squared minus 9. Now, it's not a trinomial that we have here. We actually have a binomial. And what we do is we look at the first term, and we look at the second term, and we kind of ask ourselves, are they perfect squares? And they are. 16 is a perfect squared, x squared is a perfect squared, and 9 is a perfect square. So what we have is how these would factor would be called a conjugate. A conjugate pair where we have a term plus another term and a term minus the same term. So in this case, we've got 16x squared minus 9. When we recognize this to be a difference, notice all of these are differences of squares except for C. They're all differences of squares, so differences of squares is a special product. And this is going to factor into 4x and 4x. And the square root of 9 would be 3 and 3. And since it's a difference of squares, we have to follow our pattern of conjugates. So it doesn't matter if I start with this one to be a positive and this one to be a negative, or if I flip-flopped it and this was a negative and this is a positive. So what happens with conjugates is when you check it, you get 16x squared and you get negative 12x, and then right here you get positive 12x. Here you get negative 9. What happens when we get to our four terms? We see that these two middle terms add to 0. So then what you're left with is the 16x squared minus 9. You lose the two middle terms when you multiply conjugates by one another. So 16x squared minus 9 factors into 4x plus 3 times 4x minus 3. 9x squared minus 1. You ask yourself, well, is 9 a perfect square? Yes. X squared is a perfect square. Is 1 a perfect square? So it's yes to all of them. On all those questions that you ask, you get yes on all of them. So it would be a difference of squares. Square root of 9 would be, and you could look at a square root of 9x squared would be 3x. 3x. Square root of 1 would be 1. 1. And then you could put plus, minus, or subtraction and addition. And this represents your conjugate. And remember, if you multiplied them out, you would lose your two middle terms. And then we have 4x squared plus 36. And you ask yourself, well, is 4x squared a perfect squared? Yes. And is 36 perfect square? Yes. The problem lies right here. We don't have a sum of squares. So this one is prime. Now I could factor, don't get me wrong, I can factor a 4 out of both of them and get x squared plus 9. Problem is I can't factor that anymore. So this point right here, I can't factor anymore. So I could say that that part is prime because I can't factor it. But what you've got is you got a factored form. But x squared plus 9 is not a difference of squares. It's a sum of squares. And so C is a different one of the 5 that we're looking at. C just doesn't fit the pattern of all these differences. Part D, I've got 49x squared minus 36. 49x squared is a perfect square. Yes. 36 is a perfect square. Yes. There is a subtraction, so that would simply be 7x minus 6 and 7x plus 6. If I go back to check, 49x squared plus 42x minus 42x and negative 36. Notice the two middle terms disappear and you're left with 49x squared minus 36, which is what you had in the original. So therefore, the 7x minus 6 and the 7x plus 6 that we had right over here, there is your factored form of the difference of two squares, which is your conjugate pair. And then finally, 25x squared minus 64. And remember, as we're going through the videos, you can always pause it and try these before we begin, so you can check your work as you go through the video. 25x squared is perfect. 64 is perfect. So this will factor into a difference of squares. This would be 5x here, 5x here. 64 would be 8 and 8. And then you can write your plus and minus. And you always want to check and see if you can simplify any more of these. You cannot, so you're finished. And there's your factored form. Now remember, you can always create your own. We discussed in class that you could 2x plus 3 and 2x minus 3. So you could create your own conjugate pair. And if you multiply this out, you would get 4x squared and minus 6x and positive 6x and minus 9. So 4x squared minus 9 would be what I would give you and say, is this a difference of squares? And if so, what was it factor into? Well, you actually already know the answer because you created, you created that yourself right here. So you can always create your own and check. Remember, you've got links within your videos, within your presentation. And so this is just a reference point to those. You can always click on those within the presentation and find extra practice to hone your skills. Now, we got another set of special products, but notice these are different. These are not your two terms or your binomials, and they're not your difference of squares. What we see here are 5 trinomials. So, but it still will fall in line with the thinking of perfect squares. So think about if I had a perfect square and this side was x plus 2 and it was a square, then that means this side would have to be x plus 2. So when you multiply that out, x plus 2 times x plus 2, what you actually have would be the area of that square. So that would be x squared plus 2x plus another 2x plus 4, and that would yield x squared plus 4x plus 4. This would be a difference of squares because the leading term, 1x squared, is a perfect square, and 4 is a perfect square. So let's take a look at the first one. 16x squared minus 40x plus 25. So you ask, is 16x squared a perfect square? Yes. Is 25 a perfect square? Yes. So this would factor but not into a conjugate. It would be 4x and 4x. And 25 would be 5 and 5. Now, the thing is it has to, remember, we didn't lose our middle term here. So this has to add to negative 40x. So that sign that you see here is important because that will be written in the case here. And this expression, 4x5 minus 4x5, is also equal to writing it as a quantity square. Both of these are the same. Both of these are equal. This is a more efficient way instead of writing it twice. So you see that this could be our length, this could be our width of our square. They're both the same. And since it is a quantity square, that's the length times the width, that was our area. So another one, we've got 9x squared plus 24x plus 16. 9x squared is a perfect square and 16 is a perfect square. So the square root of 9x squared, we would say 3x and 3x. And the square root of 16 would be 4 and 4. And since it's an addition sign, we would write the addition and addition, and we would get 3x plus 4 quantity squared. Now, if I want to check it, that would be 9x squared positive 12x, another positive 12x, and a positive 16. And what happens to the two middle terms? Well, we add those to get that 24x. So that just means that these two, either one, would represent the special factored form of this trinomial. (4x squared minus 20x plus 25). Is 25 a perfect square? Yes. Is 4x squared a perfect square? Yes. So that would factor into 2x, 2x, 5, and 5. And then what would be the sign that goes here? Comes from the sign of your b term, your bx. And I'm referring to this here. The bx term right here is the negative 20x. So subtract, subtract. That would be the same as 2x minus 5 quantity square. Part D, we're looking at 16x squared minus 8x plus 1. Is 16x squared perfect? Yes. Is 1 perfect? Yes. Notice I have a subtraction here. So you could, the more efficient you get at this and you recognize that it is a perfect square trinomial, you could take the square root of 16x squared and write 4x. Take the square root of 1 and write 1. And you know it's a perfect square, so I'm going to put the subtraction sign and give it a quantity square. You're welcome to jump to that part if you recognize that it is. If you feel like you need to write it out this way, that's fine. I would eventually like you to go from this point and write it in this form. That would be the final form that would represent these two factors. And then finally, got 25x squared plus 20 plus 20x (25x squared plus 20x plus 4). 4 is a perfect square. 25x squared is a perfect square. So this would factor as 5x, 5x, 2. The sign is positive for the b, so this would be positive, so we get 5x plus 2 quantity square. And those are all examples of special products that all factored as a quantity square, but all began as a perfect square trinomial. Check for understanding. Looking at number 1, you would have 9x squared minus 4, and that is a difference of 2 squares, so that would factor as a conjugate. 3x plus 2, 3x minus 2, and I cannot factor any more, so that would be the answer to number 1. Number 2 is 36x squared minus 25. That again, perfect square, 36x squared, 25 is a perfect square. It's a difference of 2 squares, so that would be 6x minus 5 and 6x plus 5. Remember, you can check by multiplying through and notice that the middle terms will eliminate. Number 3 is 3 terms, so you're checking to see, is this a perfect square trinomial? And 25x squared and 16 are both perfect squares, and this is a positive value, so this should be 5x plus 4 quantity square. Number 4, 100x squared is a perfect square, and 25 is a perfect square, so the middle term is negative, so there would be a subtraction. So you would have 10x minus 5 and 10x minus 5. Now the thing here is there's still factors within here. So we could factor a 5 out here, and that would be 2x minus 1. And we could factor a 5 out here, and that would be 2x minus 1. And remember, all this is being multiplied together. So 5 times the 5, you're going to get 25 times 2x minus 1 quantity square. Now, what could we have done in the very beginning? Is we could have factored out a 25 at the very beginning, and that would give us 4x squared. 100 divided by 25 would be 4x, and 25 divided by 25 would be 1. And so this is a perfect square trinomial, so this would be 25. 4x squared is a perfect square, so it would be 2x. 1's a perfect square, so we would be 1, and the middle term is negative, and we would give it the quantity square. So you can see that we end up with the same result. 5 is a review, and it's a review from Check for Understanding number 2, where we're going to factor by grouping. And remember, what we do is we take A times C, and we get 6 times negative 6, and we got negative 36. And then we added, they should add to give us 5. So we've got 9 and 4. 9 times 4 is 36, but they need to add to positive 5. So one's got to be positive, one's got to be negative. In this case, it's going to be a negative 4. So we've got our factors. A is not 1, so we rewrite the first term. We rewrite these two to represent 5x, so I'm just going to write the negative 4x first, then the 9x, and then you rewrite the last term. So here's your 4 terms, and then remember you group and you find your GCF. So 6 and 4, so that would be 2x, so that would be 3x minus 2, and 9 and 6, it would be 3, and you're left with 3x minus 2. So your final factored form would be 2x plus 3 from right here, and 3x minus 2.